So the last objective of this lecture was to be able to compute velocity and acceleration. And if you remember when I introduced the deformation map, so I had my reference body B naught and I have some vector x, and that one gets mapped to, this is supposed to be a trajectory, so that gets mapped to the vector b, and so I have this is my little vector x, which depends on the coordinates x and time, right? So this trace that I have right here, this one is sort of the path that this position or this particle takes as a function of time, right? So this is my trajectory of x, right? And that would be basically phi of x as a function of time. And so now I don't only care about, local deformation. So that was one thing that we were doing with the deformation gradient. Maybe another thing that I want to compute is the velocity of this particle x as a function of time. So what if I want to compute this velocity vector, right? So what is that velocity vector? That velocity vector is nothing but the time derivative of this deformation map. So the velocity vector is going to be the time derivative of this map. I guess I should make a partial derivative, and I will make explicit the dependence. So this will be a v. Note that this depends on the capital X. And that's because the deformation map depends on the capital X, right? So that's my velocity vector. Now I could express this v, this vector b, same vector v, but I can express it in terms of these deformed coordinates, right? Because as you can see here, even though v is a spatial vector, the dependency is on the big X, and that's just because I'm tracking the same particle. That's what it refers to. That's why it's in terms of this capital X. But I could always replace this X with the inverse of the map. So after I take the derivative, I can make, and I'm gonna use v with a little hat in terms of little x. So what if I want to have, instead of say what is the, so this asks the question, what is the velocity of particle that originally was at position capital X, but now at time t, whereas this one right here is asking what is the velocity of whatever particle happens to be at location lowercase x. So that is nothing but this v that I have right here, but instead of evaluating at the capital X, I evaluate at the inverse of the map, at this phi inverse of little x. And so this is the material velocity. I mean, it's the same velocity. I should say material point of view. And this is the spatial point of view. So again, note when I have v in terms of the, actually this is, I mean it's the same. So it's the same vector v, but I'm evaluating, basically what I'm saying is if I evaluate instead of capital X, I plug in, I compose with the inverse of the deformation map, then I'm gonna get a new function that is where the independent variable is the lowercase x. And so the difference is here I'm asking for what is the velocity of particle capital X at now time t. Whereas when I plug in this inverse map, what I'm asking is, what is the velocity of the particle that happens to be at point little x right now? I don't know where it was, but it's now a particle little at position little x. That's the difference, sort of where you are asking the question. So that would be the velocity. And then for the acceleration, similarly to the velocity, what I can get is I can get the acceleration in terms of the capital X t, and that is nothing but the second derivative of the deformation map, or the derivative of the velocity. Of the velocity without the hat. Not also, the hat doesn't mean unit vector, it just means I'm just using that to indicate that it's a function of the lowercase x. So that is the acceleration, but again, note that this acceleration is in terms of the capital X. So what if I want the acceleration in terms of the lowercase x? Yes, one thing that I could do is just do the same as before. So one thing would be to compose with this inverse map. And that would work. But another alternative is to use directly this v hat, which is already in terms of the lowercase x. And so what does that is called the material time derivative. It's a special type of derivative. So I cannot, the thing that I cannot do is I cannot do, let me just, so this, the acceleration is not the partial derivative of this v with respect to time. So that is not true. And why is that not true? Because x is moving, right? So the lowercase x is moving. So this is not true. The big X is never moving. So then I can take as many time derivatives as I want because the reference configuration is fixed. That one stays there all the time. So then I can take these derivatives, no problem. When I have fields that are defined in terms of the special coordinates little x, then I have to be careful, right? So I cannot use, I can definitely pick this acceleration and substitute the inverse map. That I can definitely do, no problem with that. Because when I took the derivatives here, I took the derivatives when everything was in terms of these reference coordinates, which are fixed, they don't move, right? But if I have, for example, this spatial field v hat, which is in terms of the little x, I cannot take a time derivative, and that's it. So this is not true. So this a, which, as I said, is the a composed with the inverse map, right? This is defined. If you want to use this directly, then what you have to do is you have to add one term to correct for the fact that the little x change. So I have dv dt plus the gradient of this v hat times v hat. And this comes from basically taking a derivative with respect to x hat and acknowledging that x hat changes. Right, so I'm using chain rule here. So this is the other definition for the acceleration. If you want the acceleration in the deformed configuration, but you want to obtain it directly from the velocity in the deformed configuration, you have to do this. This is what is called the material time derivative. And notice that it's not just the partial with respect to time, but it has this extra term, which is sort of a convective term. Convective term because the deformed configuration little x is changing, right? So that's it. That's velocity and acceleration in terms of the big X or the lowercase x. It's the same velocity and acceleration. It's just that